Hello everyone, welcome back. In the last video, we introduced the important notion of Lorentz transformation. Basically, this is the transformation that relates coordinate on one reference frame to the coordinate of another reference frame. So I have mu, nu, x, nu. So the matrix relating the coordinates in two frames can indicate either rotation, or boost, or a combination of both. Now this, in other words, can be interpreted as the coordinate transformation, but the point is that these are vectors not in 3 space, so they're not vectors in 3 space, but 4-dimensional space time. So that's an interesting distinction between the vectors we have talked about in the earlier videos and vectors in 4-dimensional space-time, what we call to be 4 vectors. So remember, how did we define vectors? We defined vectors. So vectors were geometric objects that transformed in a particular way under coordinate transformation. And then we generalized, we saw different kind of vectors, and all of them actually have this same common property that they transform in a particular way under coordinate transformation. Well, the Lorentz transformation looks like the coordinate transformation in 4-dimensional spacetime, which it is, right? We notice that one kind of coordinate transformation we already have common among 3 space vectors and 4 spacetime vectors. But 4-dimensional spacetime vectors, it is a bigger space, so it has extra kind of coordinate transformations, which you call boost. And of course, if we had 5-dimensional space, 6-dimensional space, there would be other coordinate transformations. So from this, we can speculate that Lorentz transformation is basically the coordinate transformation in 4-dimensional space-time, right? So then we can introduce other kind of 4 vectors, and we can use these 4 vectors as an umbrella term for those vectors in 4-dimensional space-time, vectors in 4D space-time. Let's suppose a generic symbol, for example v, mu, where mu can run from 0 to 3. So there are 4 components. So 4 vectors are vectors in 4-dimensional space-time that under Lorentz transformation transforms as b prime mu is equal to lambda mu nu b nu. That will be our definition of 4 vectors. So let me give you a couple of examples of some familiar 4 vectors. So immediately we can cite the example of 4 velocity. So what is 4 velocity? 4 velocity is basically the parametric differentiation of 4 vectors, where tau is any parameter of motion, right? So that's for velocity. We can generalize to define for acceleration, which is analogous to acceleration in 3-dimensional space, which is basically the second derivative of pole position with respect to the same parameter. We can also have 4-dimensional current. Actually, 4-dimensional current density So full current density J mu, which is defined as the scalar charge density in the time component and three-dimensional current density in the space component. So Jx, Jy, Jz. We can also have for potential. So this is basically denoted by A mu, and in its definition we have the scalar potential divided by the speed of light as a time component and three-dimensional vector potential as the spatial components. So we have Ax, Ay, Az. We may also have for force, which is the generalization of three-dimensional force, and is written as K mu, and it is defined as the mass times the forward acceleration. It is important to distinguish that we'll not refer to different kinds of masses. Normally in the old relativistic books, they introduce two different kinds of masses. One is the variable mass, and the other is the rest mass. We will not distinguish mass in this two ways. There is only one kind of mass, which is in the old literature known as the rest mass, and this doesn't change when we change the frame of reference. Perhaps the most important of all, of course, is the full momentum, typically written as P mu, and this is defined as energy divided by c in the time component and the 3 momentum in the spatial components. So at this stage, I must point out a couple of important facts. First of all, I must mention that more or less this, what we have just described here, this list of 4 vectors, these are mostly the 4 vectors we will deal with. If there is an additional kind of 4 vector, we'll immediately introduce it. And the second point is that all of this follow the transformation rule, the generic transformation rule. Now that we know about tensors, it begs the question, how does 4-dimensional tensors transform? So I'll give you an example. For example, if we have a tensor which have 2 components, these 2 are contravariant components, then for each component we'll have one Lorentz transformation matrix. So this quantity will transform something like this: lambda mu rho lambda nu sigma a rho sigma, and of course this is a transformed variable. And if we had one upper and one lower indices, one contravariant and one covariant indices, then it would transform for the contravariant index as mu rho, and for the covariant index as nu sigma. Notice that these 2 are opposite kind of Lorentz transformation matrix, and they'll be contracted with a rho sigma. So this brings us to the third point, and that is, how does the metric tensor in the Minkowski spacetime transform? So the metric tensor in Minkowski spacetime is denoted by eta mu nu, and we can write its general components as eta mu nu with 2 covariant indices. And it will transform, as you can speculate, as lambda mu rho lambda nu sigma eta rho sigma. And of course, we'll have the prime notation here. And so this is the quantity which will help us to define the inner product. So this would help us to define the inner product of four vectors. So by now it must be known to you that in Cartesian coordinate, our metric has explicit form of 1, negative 1, negative 1, negative 1. And notice that not all of the diagonal elements have the same sign, and some has positive signs, some has negative signs. And this fact that how many diagonal elements will have positive sign and how many will have negative sign will be referred to as the signature of the metric. You notice only the relative sign of the metric matters. That means I could also represent it as negative 1 and then plus 1, plus 1, plus 1. And they would describe the same kind of physics. So it is only the relative signs that matter. And often particle physicists tend to use this signature, where the gravitational physicists tend to use this signature. So it's nothing to be confused. It's just a mere change of convention, but both of these representations of metric indicate the same physics. So this is the Cartesian representation. So Cartesian representations. We know in different coordinate systems, the metric appears to have different forms, right? So, for example, in spherical coordinate system, we'll have something like 1, 1, r squared sine squared theta. And likewise in other coordinate systems. The next video, I'll talk about the inner product of the four vectors, and although I was supposed to talk about rapidity in this video, we'll see that in the next one.